This is the QTrace Analyser from PDQLogic. It's part of QTrace, a low-cost ETM trace tool for ARM Cortex-M3 and M4 processors. The QTrace Analyser is a 64-bit Windows application with three main views that are selected using the coloured tabs in the top left corner of the screen. Each view shows a different perspective of how the application is running. The source view is the default view and is being displayed at the moment. It shows the list of source files with their respective functions that are used to build the project ELF file. Clicking on a function in the list will show its implementation in the source view. On various lines you'll notice purple blocks next to the line numbers. These indicate that a line contains instructions, and so clicking on any one of these lines will display the corresponding disassembly. You'll see that at the bottom of the screen. The ELF file that's currently loaded into the analyzer is targeted for the demonstrator board, which is supplied with the QTrace kit. It's a simple USB flash drive application that shows up as a removable disk when it's plugged into the PC's USB port. So I'm going to show QTrace in action now. On the other screen is TrueStudio from Atomic. This was the IDE which was used to build the sample application. So switching back now to QTrace, let's go to the main entry of the program, and what I'll do now is I will start the processor going from within TrueStudio. After a couple of seconds of the processor running, the QTrace display has now changed. We have execution counts in this yellow column. We also have at the bottom of the screen the processor speed now shows 168 MHz, whereas previously it was 16. The average MIPS is 97, and we've executed 63% of the instructions in the build. Also, you can see on the right hand side of the screen there's a heat map which shows the activity, or where the activity has occurred in the current source file. Coming back to the numbers in the yellow column, these are referred to as code coverage, and they show exactly which lines have been executed and how many times. By arranging the if statement on line 76 into multiple lines, it's easy to see which conditions have passed. Also, on line 78, as expected, the call to start the scheduler did not return. If it did, then there would be a count on line 81. So when chasing down a bug, it's incredibly useful to have this kind of information, and it's a bit like being able to single step through your code but at full speed. Another really useful feature of code coverage is the ability to generate an execution rate, which is very helpful when verifying loop timing. I'll navigate to the system tick handler, which has been set to a 1 kHz rate. You'll see that by hovering over the code coverage area, a pop-up appears showing how often the line of code is being executed. You can see that the sysTick handler is indeed being executed at a 1 kHz rate. You can do this anywhere, and it avoids having to modify your code to toggle an I/O line and then viewing it on an oscilloscope. The next feature I want to show is the ability to generate a call stack from any line of code being executed, but without actually stopping the processor. By highlighting a line and then pressing F9, a snapshot of the last 8 million instructions will be captured when the line is next executed. These can then be reviewed while the processor is still running. I'll browse to a function that has a reasonably deep nesting, and then I'll generate a call stack. So I'll select a line, I'll press F9, and you'll see that the purple block next to the line number turned brown, and then the display will switch to the trace view when it's triggered. So we've now switched to the trace capture display. There are three distinct views here. The first is a list of 8 million instructions that were captured prior to the trigger. The second is the source that corresponds to the selected instruction. And the third is a timeline showing the call stack where each horizontal red line represents time spent in a different function. By default, the timeline displays the last 64,000 instructions, but the entire 8 million can be used to generate the timeline if required. The rightmost position of the timeline represents the trigger instruction, and the instructions prior to this are viewed by going from right to left. So you can select individual instructions on the timeline, or you can scroll between function transitions. You can also zoom out as well as manually scroll the timeline. So you can see here that the processor is not doing very much, and then come back to our trigger point and we can see quite a bit of different activity. The trace capture display is also used to show the execution history prior to a CPU exception. After a processor reset, the QTrace Analyser is automatically configured to detect CPU exceptions, and if one is detected, it will freeze the last 8 million instructions prior to the event. This allows the history prior to the fault to be displayed and for its cause to be quickly located. When the button on the demonstrator board is held for 1 second, the firmware will generate a hard fault to show the exception capture feature. I'll hold down the button now and you'll see the trace capture change to display the fault and the history leading up to it. The hard fault has now been detected and the captured data prior to the fault is now loaded. I'll scroll to the trigger point and zoom in to show the functions leading up to the fault. You can see that the last instruction is the hard fault handler, and by stepping back you can see the location of the fault. This is caused by a deliberate read from a non-existent memory location. It's a simple example, but for a complex multi-threaded system, having a large history leading up to the event can really help understand why the fault occurred. QTrace also provides user-defined triggers to generate an execution history for other address ranges of interest. They're in addition to pressing F9 and the CPU exception trigger that I've already demonstrated. These settings can be found in the Trace Capture tab at the bottom of the source viewer. Each trigger can be either source or address based and defined as single or multiple lines or addresses. Here, trigger number 1 is defined as a range of source lines which also happen to be the CPU exception handlers as defined by this checkbox. This was the trigger that was used to capture the hard fault shown previously. Source-based triggers can be located in the source view by pressing the View Source button. The trigger range is highlighted as red blocks next to the line numbers. I'll configure trigger number 2 to capture trace when a particular source line has been executed 3 times. The line I'll specify is executed when the button on the demonstrator board has been released. I'll browse to the line and select it to be used for the trigger. So line 265 is the line to use. I'll select trigger number 2. You'll see that the range is automatically set to a single line. I'll change the hit count to 3. Click apply. So now that the trigger has been configured, you'll see that the purple block on the margin has now turned to green to indicate that a counting trigger exists on the line. I'll now press the button 3 times, and with each press you'll see that the line has been executed, and on the 3rd press the trace will be captured. So that's the first press, 2nd, 3rd press, and as you can see the trace has been captured. And it's been captured on line 265 up in the source view as expected. The final view to demonstrate is the profiling display. It shows the functions in which the processor is spending most of its time, and a quick glance can reveal information that just isn't possible to see with conventional debugging. I'll switch to the profiling tab, and here you can see a list of functions which are included in the build. This information is extracted from the ELF file at startup. You can see that for each one of these functions there are several statistics. There's the total number of calls made to the function. There's the percentage of instructions in the function that have been executed at least once. And then there's the total time that the processor has spent in the function. I can double click on any one of these functions and see its implementation in the source view. I can also generate a call stack for any function. So there we go, there's a call stack as we've seen before. I can also display just the interrupt handlers to see which interrupts are occurring and the rate at which they're happening. So if I go over to the right hand side and select sort by interrupt handler, and you can see that there are 3 interrupts that are regularly interrupting and another 3 which have happened but are no longer happening. Again, I can double click on any one of these handlers and see the rate at which the code is being executed. So here we are back to the sysTick handler, and again, as expected, that's interrupting at a 1 kHz rate. Lastly, the QTrace Analyser has an integrated ITM debug viewer. This is essentially a terminal emulator window which displays debug messages output by the firmware. Instead of requiring a separate UART and an RS-232 lead, the firmware writes to a specific processor register to insert user-defined strings into the trace data stream. So I'll restart the processor to show the startup debug messages and the subsequent timeouts output by the demonstrator firmware. So I'll just switch across to True Studio. Processor's almost reset. So it's reset now, but before restarting it, I'll display the ITM viewer by clicking on the green terminal icon. So that way the startup messages you'll easily see. So I'm going to restart the processor. And there we go. We've got some startup messages there, and then it just periodically every second just outputs a timestamp. That concludes the demonstration of the key features of the QTrace Analyser. Hopefully the video gives you a flavour of what QTrace can do and how it can accelerate your firmware development to save you time and money. Within minutes of using QTrace, you'll start to get an insight into your application that you just won't have seen before. And after using the system for just a short period of time, we're confident you really will find it an indispensable debug tool.